Hello, and tonight we're at the British Science Festival here at the University of Warwick, and we have gathered together a panel of some of the finest astronomical minds who are going to answer your questions about the night sky and the mysteries of the universe. It promises to be a fascinating hour, a mind-bending hour for me, our audience here in the studio, and hopefully for you at home. Welcome to The Sky at Night. Thank you very much. Good evening, and welcome to a very, very special edition of The Sky at Night here at the British Science Festival at the University of Warwick. And I'm delighted to welcome our esteemed panel who are hopefully going to try and answer some of your perhaps difficult questions about the mysteries of the universe. Some of them are familiar faces. First of all, Chris Lintott, Professor Chris Lintott at the Oxford University. Long-term Sky at Night presenter, but actually more interesting than being a Sky at Night presenter is the fact that you are the 410th best real tennis player in the world.
I lost at the weekend.
Really?
So I'm
you're 411 now?
Dropping. You've
been obviously a presenter of the Sky at Night for a long time, for a few years, but actually, I say a long time, all the way back, almost 20 years was your very, very first appearance.
Yes, when in the year 2000, I did an old studio episode. It was a question and answers show. We had viewers sending questions and we tried to answer them.
And actually, when you look at that, you've hardly changed at all. We've got a little clip of it here. This is...
We did everything from why are there seasons to why is the expansion of the universe speeding up, and I only answered one of those questions well.
To my left, Maggie Aderin-Pocock, space scientist and other Sky at Night presenter. Now, you're a space scientist. You actually designed instruments for telescopes, sophisticated instruments for big telescopes.
Yes.
Do you have a favourite telescope that you worked on?
Yes, Gemini South.
Which was?
So Gemini South, there are two telescopes, one in Hawaii, which I had to go and visit, but one in Chile. So Gemini South, an 8-metre telescope, so one of the largest telescopes in the world. And
this is it, here we go, beautiful views.
Yeah,
this is Chile.
Yes, I was working at UCL and I built an instrument called BHROS, which stood for Bench Mounted High Resolution Optical Spectrograph. Bit of a mouthful. That's why we called it BHROS. So I built that in the basement of UCL with my team, and then we shipped it out to Gemini South. And I spent an amazing 6 months working out there. And every night I'd have a glass of Chilean wine and watch the stars appear in the night sky.
That's the place to go and look at the stars in the Chile, Atacama.
Yes.
Clear skies, wonderful, wonderful.
It was amazing.
To my far left, Pete Lawrence, the doyen of amateur astronomy, a man who needs his space.
I need my space.
And Sky at Night presenter. Now, what was it for you that got you into astronomy? Was it a thing, a person, an event? What was it?
I think both my grandfathers were into astronomy, and I think that rubbed off really. But my parents bought me a small telescope, which I went outside. It had a tabletop mount, balanced it on a stool, looked at a really bright object in the sky, saw it had a disc with 4 dots next to it, looked it up in my observer's book of astronomy, and the closest match I got was Uranus. So I thought, yes, I've seen Uranus. Of course, it was Jupiter.
But from then on, that was it. You were
absolutely hooked.
You were hooked. Fantastic. Now, we've got 2 special guests with us tonight as well. Farzana Maroo, astrophysicist from here, University of Warwick. Now, you're interested in theoretical modelling of protoplanetary disks. So for the uninitiated, what do we mean by protoplanetary disks?
So protoplanetary disks are basically the birth environments of planets. So once upon a time, our solar system would have had a disk of gas and dust surrounding it. And it's out of this disk that the planets in our solar system would have formed.
Well, thank you very much for being here. We're going to, I suspect, come on to a little bit more of that later on. And finally, we have Lee Fletcher, planetary scientist from the University of Leicester. Now, you were involved in the Cassini mission to Saturn. which we've heard a lot about on this programme. But you're involved in a new ESA project as well called JUICE.
That's right.
Explain what JUICE means.
So JUICE is the European Space Agency's large class mission. It's going to launch in just a short few years' time, 4 years, to the planet Jupiter. And it's going to be exploring Jupiter and all of the icy satellites surrounding Jupiter, including places like Europa and Ganymede. So lots of exciting stuff.
These are places we've wanted to go to for a long time and explore
They're
more.
fascinating places. We might talk a little bit more about them later, but they might harbour oceans down beneath their icy crust, which, who knows, could be the right place for us to go and look to search for evidence of life.
Fantastic. And that is our panel. Okay. Judging by the thickness of my question cards, I suspect we better get on. Okay, so first question, and this is from somebody in our audience here at Warwick. It's Margaret Bloomer. Where's Margaret? Margaret, could you give us your first question, please?
Yes. Good evening. Anybody who has witnessed a total solar eclipse will understand how addictive they can be, as everyone is different. I went to La Higuera, Chile, to see my fourth on the 2nd of July. My question relates to the mirrors left on the moon's surface by Apollo 11, which have been used accurately to measure the Earth-Moon distance ever since. As a result, we've discovered that the moon is gradually spiralling away from us. Total eclipses, therefore, will gradually become rarer. Do we know when the last ever total solar eclipse will ever be?
Thank you very much for that question. What a fascinating question. And we have our little tribute to the Apollo 11. We have a replica of Neil Armstrong's spacesuit. And actually one of the, as you mentioned, one of the first experiments they did was put down these mirrors. Maggie, a moon expert, as you are, just tell us a little bit about these mirrors. What are we actually talking about?
Yes, as part of the Apollo programme, they left these mirrors called retroreflectors on the moon's surface, and with the express idea of measuring the Earth-Moon distance. And so I was very lucky. A few years ago, actually quite a few years ago, I went to Apache Point, where they have a huge laser, and they beam that up towards the moon, sending billions of photons up there, and then we get a few coming back. And by looking at the time of flight of those photons, you can actually work out the distance between the Earth and the moon. So they've been doing this for over 40 years now. And now they've worked out that the moon is very slowly moving away from us. And it's moving away at sort of about 3.8 centimetres a year. So not very much, but that's about the same rate our fingernails grow. So just to put it into perspective. So the moon is slowly drifting away from us.
Pete, and what does that mean for our beautiful solar eclipses, which of course are a sort of cosmic coincidence, really, the sun and the moon disks in the sky being the same size. And if the moon is gradually drifting away 3 centimetres a year.
It's quite a difficult thing to work out, but it's estimated that the last total eclipse of the sun will occur, it's about 580-something million years' time. There are other estimates that say that's when they will sort of start to become, or start to stop, if you like, and then they will finally end about 1.2 billion years into the future. But it's a difficult thing to quantify, really, because in a way they are stopping at the moment, because we have annular eclipses where because the moon's orbit around the Earth is not a circle, it's an ellipse, so the apparent diameter of the moon does vary over time, and also because the Earth's orbit around the sun is an ellipse as well, so the apparent diameter of the sun varies as well. So if the sun appears very big in the sky and the moon appears at its smallest, then the moon will actually fit inside the sun's disk. That's an annular eclipse, or a transit of the sun by the moon.
I think Margaret's angling for a date, though, to be honest. She wants dates and times and places.
July the 17th. No, I mean, the issue is that far into the future, if we still exist, hopefully we'll have the technology to actually be able to hop on a rocket, or whatever the equivalent will be, and pop up there and just organise our own total eclipse of the sun.
Just to be clear, that's definitely cheating.
It's not cheating
Half of the
at all.
magic of these things is that you're at one place on the Earth's surface at a particular time, and you get rewarded with this particular sign. I don't think I'm not buying your artificial eclipse tour.
Well, if it's not happening, you can't do it.
It would be fabulous for astronomy, because you'd be able to sit there in the shadow of the moon at all times, being able to see the night sky out in the
point.
opposite
Yeah,
direction. So I think that alone is the reason to do it.
Does that kind of answer your question?
Yes.
Happily, good. I've got another question. This is actually someone that's been sent in. James Wilkins from Southampton. I'm reading it out because it's related. I've heard the moon is receding from the Earth, about 3 centimetres per year, as you said, Maggie. What I'm wondering, does this apply to planets orbiting the sun, our planets? Are they receding, or would it depend on how massive the planets are? In which case, are we being attracted inwards, Lee, as our planetary scientist?
Yeah. So we're in an era now where when you look out at the planetary orbits, it appears relatively stable, but I think that's more a product of our short human lifespans of a few tens of years or so. You look at somewhere like the moons of Saturn or the moons of Jupiter, for example, and you can see this constant gravitational tugging and pulling that means that those satellites don't always remain in exactly the same place. The satellites of Saturn are slowly moving outwards. And another great example is Triton, one of the largest satellites of Neptune, which is actually slowly moving in towards Neptune itself, and one day will be broken apart and turned into a new ring around Neptune. So that stability that we seem to see today is actually just an illusion, and things are always changing.
Fazana, when you're doing protoplanetary disk modelling, can you find anything about orbits even that early on?
Indeed, so the orbits of the planets do in fact change over time. So in fact, in the protoplanetary disk, the planets actually interact with the disk, and this kind of interaction actually causes what we call planet migration. So planets can actually move both inwards and outwards, but generally inwards towards their central star.
I think we've got a little VT, actually. I think
Do
we've
we
got a
actually
little
have
rotating planet VT. Here we go.
We
Yeah,
do.
so this is your world, as it were.
This is my world, yes, indeed. So it's one of my students' simulations where he's actually showing a planet moving inwards into the inner part of the protoplanetary disk. Now,
So this is early solar system.
this is very,
birth of the
very
solar-
early stage, yes. When the planets move in rapidly, this can be on the order of 100,000 years. That's something called type 1 migration. Very, very unimaginative. The second type of migration that we have is called type 2 migration. So this is
Clever.
So this is when the planet becomes massive enough that it can actually open up a gap, and you can see that in this in the simulation here, where it actually opened up a gap. And when it does that, it actually moves so much more slowly. In fact, so from about Neptune to the inner part of to the Sun, it would take about 10 million years, which is up to the lifetime of the disk. So that means that the planet moves in.
Chris, can I ask you, our solar system particularly, are the planets now different to how they have been in the past?
So they certainly changed in the early days.
Yeah.
We're learning that those early stages were chaotic. I think right now the main thing that's happening to the Earth, if we care about our planet, is that the sun is actually using up its mass because it's through nuclear fusion. That's what powers the sun, and so we move very slowly outwards. I think it's a bit less than the moon. It's about a centimetre or two.
1.5 centimetres.
About half a centimetre. Yeah. So that's what's happening, but there is at least one group of researchers who have looked into the far future with computer simulations who think that the solar system could be unstable. So the orbits of the planets could change dramatically over the course of probably hundreds of millions of years or something like that. Now, if that's right, that's bad news for long-term survivability on Earth. And it may be that we've just been lucky and we've ended up in a solar system that is, to date, stable for the long run.
Fantastic. Right. Thank you very much indeed. Right. Our next question from the audience, Ian Metcalf. Where's Ian? There he is. Ian, what's your question?
Given the random nature of meteors and the fact that when we see them in the night sky as shooting stars, they always seem to be travelling across the sky rather than directly to the Earth. So why is it that all the impact craters on the moon all seem to be circular, which suggests impacts of a vertical nature? The moon has a very low gravity and no atmosphere to slow the meteors down. So why do they all seem to impact vertically?
I'd never even thought of that, but it's a very good question. Why are comets not elliptical? Pete, come on, you're
Why are the
you're a
craters
crater
not elliptical?
What comets? Craters, excuse me.
The reason is basically as the impact occurs, it's like a massive explosion that happens, and the explosion goes off in all directions symmetrically. So it creates a crater which is effectively circular. But there are examples of craters on the moon which do look elongated.
I think we have a picture, or we might have a picture. There we go.
There's a
this is,
classic.
this
That's
is on-
Schiller.
Is this on the moon?
Yes, it is. That's Schiller, and that looks definitely elongated. But it's really fascinating to look at these features and try and work out what's going on. And if you draw a line along the long axis of that crater, it points back to a huge impact basin, which is Mare Orientale, which is absolutely beautiful, but we can't see it properly from Earth because it's just round the edge, very frustrating. But what's probably happened here is that a number of bodies have all hit at the same time and formed this elongated crater. So they've all exploded together.
Lee, now you've got a favourite crater on Ganymede, I think.
Yes.
An elliptical
There's actually
crater.
this
Is it this
fantastic
one?
image of a crater on Ganymede where it shows those two processes at work, because each of the individual craters have been formed by the sorts of micro explosions that Pete was mentioning about, where everything's moving out equally in all directions. But there's obviously been so many impacts in a straight line just there. It creates this large gash across the surface of Ganymede out there in the outer solar system.
There's an interesting feature on the moon which always makes me laugh. It's another sort of fun fact almost. It's a crater chain.
Better be fun, Pete, otherwise this is your last chance.
It is. Hold on to your sides. It's basically a very long chain of craters called Catena Davy. It's associated with the Davy crater. And what I like about it is you can see all the craters individually. They're very small. They're about a kilometre or so across. But the cartographer who drew the map of that area decided he was going to name those craters common names like Alan, Susan, Harold. I think there's a Priscilla and a Delia there. And they actually got through the process of becoming official. So those craters do exist on the moon. You can look at the moon and look at Susan and Alan.
Wouldn't that be a brilliant location for a lunar base? You know, calling Susan, this is Alan.
I'm moving. Yes.
That would be good. Right, we've had some sort of planned questions from the audience, so our panellists sort of roughly knew what you might be asking. But we've got a kind of a mystery tombola round. As I mentioned, we've got a replica of Neil Armstrong's suit. I really wanted to tell you it's the real suit. The real suit, of course, is in the Smithsonian in Washington, D.C. But in our replica Neil Armstrong helmet, we've got some mystery questions, of which you don't know what they are.
Hooray.
So who's going to go? Maggie, have a little rummage.
I'm going in.
Have a rummage. And the rule is you've got to have a stab at it, no matter what.
That's what it says.
Okay.
Well, I'm dyslexic, so I might have difficulty reading it,
Well,
but let's
we
see.
can help you out.
Reports in the news this week say an exoplanet has been found with water on it, and that eventually... analysis of its atmosphere could... Sorry.
I said could show if it has life on it.
Okay.
What gases would show this, and can that show how developed life is? P.S. Dallas is great.
Maggie is great. So this exoplanet was particularly exciting because it sits in the habitable zone around its star. So it had the potential of having liquid water. But we also had, it was in the right orientation. So as the sunlight was passing past the planet, some of it went through the planet's atmosphere, and we were able to do a spectroscopy and look at the chemical elements in the atmosphere. And this analysis revealed sort of water vapour. If you look at life here on Earth, we believe that life here on Earth requires water. The fact that we've found sort of water on this planet is very exciting.
It's a mind-blowing thing that the fact that we can look at starlight coming through an exoplanet's atmosphere and tell what's in it.
It's really difficult. This is a really complicated, and actually two groups of astronomers had a go at this at the same time, and their results, they both found water and they're not sure they agree with each other. One group says it's raining, the other group says they can't see any sign of that.
Let's call the whole thing off.
But
can't stand on this, but we think it's a gas planet, don't we?
Yeah, that's right. So
there's
this planet's
probably
8 times the mass of the Earth.
Okay.
So that means it probably doesn't have a solid surface. It's not rocky. It's sort of a soggy Neptune, if you will.
What's really interesting about that particular planet, actually, is that it's within the habitable zone of its star. But something to point out is that, just so that everyone's very clear, it's a planet around an M dwarf, which is not the same as our sun. So we're still yet to actually find, an Earth-like planet around a star which is similar to ours.
But that's exciting because it's easier to find planets around these small, faint red stars.
Absolutely,
And so if we can find planets that are interesting around those, then we might have a chance of following
and then we have more chance of actually understanding them and understanding what more about habitability. But then sort of looking towards the future, there's missions like Plato, which are really going to be able to try and tackle that question of, are there Earth-like planets around stars
Maggie, very quickly.
like our
But
sun?
your question was asking if we can confirm life, and I think we don't have the technology to do that yet. It's a sort of tick in the box. It's in the habitable zone. It has liquid water. It is around. It's orbiting a sort of a star that's giving out lots of radiation. So it's unlikely to have life there. But we don't think we have a test that we can do at the moment that will actually confirm there's life on another planet.
Very quickly, do you get frustrated as academics when the press starts going on about life?
I think we do it as scientists as well,
Excellent.
so it's our fault too. But I think all planets are interesting, right? And I got a bit frustrated when this news came out, because I care about this planet even though it's the size of Neptune, because it's interesting. Understanding atmospheres of these planets tells us about how planets work. It tells us about how our own solar system works. And I think instead people go, we found a planet. Could I live on it? No. Tough. Fine. Done. And yeah, that's frustrating.
Okay, we're going to move away from the moon. We're going to move away from planets. We're going to start talking about the big stuff. And I'm looking for Mike Carter. So what's your question?
Well, I'm always being told that light from very distant galaxies has been travelling towards us for very long periods, often large proportions of the life of the universe. But my question is, if light started that long ago, the universe then was an awful lot smaller. So the position where Earth would one day form was much closer. So why hasn't that light already gone past us?
Gosh. Okay, thank you. I think I understand the question. It's the expanding universe is one of those things that is just almost impossible to get your head round in an intuitive way. Chris.
So yeah, thanks, Dallas.
I'm gonna let you tackle this.
So I think it is difficult. It's difficult just because of this fact that the universe is big, and it was big even early on. We see only a tiny proportion of the whole universe, we think, and light takes a long time to travel across it. So light travels about a foot per billionth of a second, which means if you hold your hand here, you're seeing it as it was a billionth of a second ago. I said that at a music festival, and 10 minutes later there were still people sort of looking at their hands. We see the sun as it was 8 minutes ago. We see the Andromeda galaxy as it was a couple of million years ago. And the earliest galaxies we've seen, you're right, we see them as they were about 13 billion years ago, most of the way back to the beginning of the universe. But there's nothing special about those galaxies. So if we want to know the rest of their history, we just wait. The light that tells us the next 13 billion years of their story is already on its way to us. And if we wait long enough, then we'll see light from galaxies we haven't even been able to look at yet, because there's light from the first stars in many, many more galaxies on its way to us, and so it hasn't reached us yet. And so the answer to your question is that the universe is so big that we're still only seeing a tiny portion of it. If the universe had been really rather tiny, then we would have reached a point where we no longer saw galaxies that were nearly as old as the universe, but we haven't got to that point. The universe is big, Dallas.
Basically, you just got to wait
Yeah.
a long time for your answer. Fazana, I mean, how do we know that the universe is expanding? It's a thing that we all hear about, but where does the evidence come from?
Yeah, well, we definitely, we know it's expanding from just by kind of calculating something called the Hubble constant, right? That essentially tells us that the universe is expanding. We're looking at where it's expanding, the directions in which it's expanding, and the rate at which it's expanding. And we know from our studies that actually the university is
expanding. No, that's different.
We are expanding here. The universe is expanding, and it's expanding in all directions. So something that we call isotropically. It's expanding the same in all directions, wherever we look at it from in the universe.
That's the thing that's really struggles
mind-boggling.
to get your head around, I think, that no matter where you are, it looks the same. I've got a question which has been sent in from Vince Brandon. His question is, if everything in the expanding universe is moving away from everything else, as you say, how can the Milky Way galaxy be on a collision course with Andromeda?
Well, this comes back to this idea that it's a slow expansion,
Yes.
right? So that locally, we don't feel the effect of the expansion at all. And we know this because I'm not getting any larger. Actually, we've seen evidence. I am getting larger, but it's not due to the expansion of space. The Earth isn't getting any bigger because of the expansion of space. Because the thing that's important for the Earth is its gravity. Locally,
Can I
gravity.
just say, so the Milky Way, that's our galaxy. So
That's
we're
right.
talking about a galaxy coming towards
Andromeda's
us.
the next
Right.
big galaxy.
Big galaxy, and it's on its way.
Yeah, it turns out the two are on a collision course. We've
Right.
got spectacular animations that show what will happen when the two collide. But that can happen because
we
they
have a
gravitate. Here we are.
Here we are,
This
spectacular animation.
This starts about 3 billion years in the future. And what will happen is that the gravity of the galaxies can overcome the expansion and draw them together, and it will be the spectacular collision. So the two will collide. What's remarkable is there's enough space in the galaxies that no two it's very, very unlikely that any two stars will collide. But the gas in the galaxies will get shaken up. You get a burst of star formation. It will be a beautiful show. The night sky in about 4.5 billion years' time will sparkle with
Ron will
stars.
still be here then.
Yeah,
He's
yeah.
waiting for his
We'll all be waiting for our eclipse. And then it will combine into a single galaxy, which I'm afraid to say some of the astronomers who've calculated these things want to call Milkdromeda, which I think is an unpoetic and hideous name.
We'll let them off. That is my favourite fact. You have these. When you look at galaxies, they look as if they are made of lots of stuff, and they are. But the fact that they are going to collide and nothing will touch each other, they will pass through each other.
Space is
empty.
big.
Space is big. Okay, it's your turn for the Neil Armstrong Mystery
Wow.
Question Challenge. Are you ready
I am.
for your?
Let's have a look.
Have a little rummage around and see. That wasn't a rummage. That was a. No, that's okay. No, you can have that one.
Can I
It's too late.
decide whether
No,
I want
no,
it?
no. Do we know who the question's from?
Ganesh Viswanath. Can I repick? There are thousands of defunct satellites, space debris, is what we call them, orbiting the Earth. There are no property rights and no incentives to bring unused debris back to Earth. What solutions do you propose? Is that what solutions do I propose?
Yeah, you personally.
Yeah.
Right now,
We
this
need it
second.
soon. We've been waiting for somebody to solve this problem, so this is good.
Well, they've been. We have some solutions that have been tested out, haven't we?
we have.
Nets and harpoons that have
Yes.
gone up.
CubeSats and things like that.
It's a real problem, though, isn't it? I mean,
it is a problem.
1957, we had one artificial
And
satellite.
it's becoming a bigger problem because SpaceX and a few other companies want to launch enormous constellations of satellites, so tens of thousands of satellites to do things like provide rural areas with internet and so on. So it is a problem, but we have been testing solutions. There's a great little CubeSat whose name I can't remember, but which in the last year has been trying harpooning and
this is
netting
recent.
satellites.
Yeah.
So it's like a little satellite hunter, and it goes up to the defunct satellite, grabs it, and
And sort of brings
drags
it down and
out.
burns it up on the atmosphere.
My favourite bit, actually, it's called Point Nemo in the southern Atlantic, which is the sort of the southern point of inaccessibility, which is the most remote place on Earth. It's the point on Earth furthest away from any land, any civilization. It's also called the spacecraft graveyard because it's the place where they deorbit, spacecraft, space station, satellite, like the Mir space station, what have you. I've always wanted to go there and see what lurks
go
beneath.
just swimming
and,
around.
I'm just a bit concerned about this satellite graveyard and how long they're going to be up there, because I don't want to be looking for the very last total eclipse of the sun.
Something whizzing past. Actually, we often see sort of animations of this space debris, sort of surrounding the Earth, and it looks like sort of like a huge sphere of stuff moving around. But you've got to bear in mind, even a large satellite is about the size of a double-decker bus, and but on the scale of the Earth, that's less than a pinprick. And so they scale these things up so we can actually see them. So it isn't half as bad as that. And with this designation, we are sort of trying to keep control of it, and we are coming up with solutions. I think the Japanese were coming up with a sort of a space net, to muster lots of them together and then sort of deorbit them and burn them up as shooting stars, which would be very pretty.
But I think where we need to get to is the point that you have to have a plan before you launch, and you have to have a plan before you launch, even if your spacecraft breaks.
That is the case now. So when a satellite is launched, it's given this designated cube in space, and it has to it signs up to actually maintaining that cube. The problem is that if something goes wrong, then you're not in control of your satellite anymore. It collides with another satellite and sets up even more space debris, which then goes into orbit and collides with other things. So it's accidents that are mainly causing this problem, I think.
Yeah, things like flecks of paint, which are like bullets going through it, do a hell of a lot of damage.
Yeah,
So-
there's a tool bag somebody
Tool
dropped
bag,
from the
a
space
spatula,
station. The
there's a spatula.
spatula's tumbling.
A
Yeah.
tub of ammonia, I
An
believe.
Orlan spacesuit was thrown out of the International Space Station with all kinds of things. Anyway, we could go on and on. We won't. Okay, well, as well as pondering the mysteries of the universe, we're also interested in what we can see in the night sky. So it's over to Pete. What do we have in store for the next few months coming into 2020?
Well, I've picked a number of things which are fairly, hopefully fairly easy to see, and hopefully will give you an impetus to go out and actually have a look for yourselves. But I'll start with an event which is probably the highlight of the amateur astronomy calendar for 2019. And it occurs on the 11th of November, when the innermost planet in our solar system, Mercury, will start to move across the face of the sun. And that's an event known as a transit of Mercury. This starts at exactly 12:35 and 27 seconds, so don't be late. It takes 5.5 hours to watch this little dot move across the face of the sun. The event actually ends at 6:04 in the evening, but again, because it's November, the sun will have set by that time. So we'll lose the sun about 4:20. Now, these events, or transits of Mercury, are pretty infrequent. The next one won't be until November in 2032. Now, Mercury is pretty small when it crosses the sun's disk. It's about a sixth of the size you need to be able to see it with the naked eye. But you will need to use binoculars or a small telescope at least to be able to pick it up. But again, you need to be really careful. You need to make sure you use certified solar safety filters fitted to those telescopes. Okay, so the next event I'm picking on is actually the outer neighbour to Mercury, and that's the planet Venus. Now, when Venus appears in the evening sky, if the timing is right, it can be pretty spectacular. Look behind you, and you might actually be able to see the faint shadow that Venus is casting of you against whatever you're looking at. But because it'll be in the evening sky, every month Venus will get a visit from the waxing crescent moon. And the waxing crescent moon and Venus together is an awe-inspiring sight. It's one which a lot of people try and go out and take photographs of. So get outside and actually try to do that if you can. So the final item I'm going to mention to you, I'm taking a bit of a risk on with this one because it is a comet. And comets are a bit difficult to predict. They're often said to have the same predictability as cats. We know how difficult they are to predict. Comets, there are always lots of comets up there in the night sky. Most of them are really, really faint, and you need a big telescope or an imaging system to be able to pick them up. Occasionally they'll become bright enough so you can see them with a small telescope or binoculars, and very rarely they get bright enough that you can see with the naked eye. From now through 2020, or the early part of 2020, we have a reasonably well-placed comet that is predicted to get close to the threshold of naked eye visibility. And being that close, it could get brighter, or it could get fainter, who knows. But we can only hope. Now, this particular comet is called C2017 T2 Pan-STARRS, which is pretty catchy. It will be in the northern part of the sky, so it'll pass very close to Polaris. It's going to also encounter a couple of nice deep sky objects up there. As we get towards late January, it will pass a couple of open clusters known as the double cluster, or the sword handle in the constellation of Perseus, the Greek hero. And that'll be great to locate the comet. It gets to its brightest in early May, and then towards the back end of May, it will pass two very popular galaxies, fairly bright galaxies called M81 and M82. That's Bode's Galaxy and the Cigar Galaxy in Ursa Major, the Great Bear. That's a good time to get out there, try and find the comet, and try and take a photograph of it if you have that sort of equipment. So I hope that will give you a bit of incentive to go outside and look up at the night sky. Thanks.
Thank you very much, Pete. As ever, lots to look up and look forward to coming up in the next few months. Next question, we're going to move on, is sent in by me, actually. This is a question that I've actually been worrying about. We've mentioned this 4,000, we've crossed the 4,000 exoplanet number now, so we're understanding much more about exosolar systems. And I was wondering just how common or unusual is our own solar system, given we now have this extra knowledge about exoplanets?
Yeah, so that's definitely a question a lot of people are asking, in fact. The short answer to that is, at the moment, we think that the solar system is quite unique. We can think about this from a couple of different perspectives. So from the protoplanetary disk perspective, we've observed these wonderful protoplanetary disks with lots of really, really exciting features. And many of them have got gaps and rings. So here's one example of them. If we just look at the planetary system on the right-hand side, that is our solar system to scale compared to the HL Tau protoplanetary disk.
And those are the outer planets we've got. Those are the orbits of Jupiter, Saturn, Uranus, and Neptune.
Indeed,
right?
indeed.
So we're a bit smaller.
Definitely. When we actually look at those gaps and rings, we can actually try and get some kind of an estimate as to what the mass of the planet would be that would be in those gaps. And what we're finding is that actually most of those planets are actually much larger than the terrestrial planets in our solar system. They're what we call super-Earths, or in fact giant planets. Now, that isn't to say that the planets that form in protoplanetary disks like this wouldn't end up being like the solar system, but the fact that we're estimating that the mass of those planets are more like super-Earths, so that's about 10 Earth masses, does tell us that things are very different.
The beautiful thing that you're seeing in that particular image is that you're looking at the birth of these planets, right? Whereas that 4,000 number that, Dallas, you were mentioning before is a census of planets that are sort of fully formed, fully fledged, and are out there orbiting their stars now. And when you look at the statistics, that's something you can now start to do with this 4,000 odd planets that are out there, is you can see the most common outcome of the planet formation process. You can't do that just by looking at our own solar system, because you'd be misled. And when we do that, you start to see that these super-Earths and the mini-Neptunes that you were mentioning seem to be the most common types of planets out there.
So we are quite unusual then.
You look at our solar system, we don't have one. And the question is why?
And is that partly due to the fact that we just don't have the technology yet to be able to see smaller planets?
There could be a bias, that's certainly true. But we are increasing that census all the time. We've got new missions that are going to be launched in order to look out at other stars to see whether we can probe down to smaller and
smaller. Do we know how many stars have actually been looked at yet?
To get the 4,000?
No, the 4,000 planets, but how many stars have been studied?
That's a difficult question, because you have to think about, a lot of the methods used are indirect, but when you do the calculations, you come up with no doubt that planets are really common. I think what surprised me and surprised a lot of people has been the diversity of the planetary systems we found. That I think we thought, if you look at our solar system, you can read textbooks written 10 years ago that tell you that you get a nice array of rocky planets, Mercury, Venus, Earth, Mars, close to the star, and then bigger planets further out. That's not a universal rule, it turns out. We've seen hot Jupiters, we've seen systems spread out like this one, we've seen systems like the TRAPPIST-1 system, where the planets are crammed in close to their star. I think if we'd known a long time ago that there was this diversity of planetary system out there, we could have found these a long time ago. Part of the reason it took us to the mid-90s and beyond to start really finding these exoplanet systems was that we thought we were looking for systems like our own.
Yes.
And finding small planets like the Earth or planets that are further from the star is a much harder task.
And in fact, actually, there are. In fact, we might even have a movie of one of these. The HR8799 system actually has 4 very giant planets. This is real, this is amazing. I was absolutely mind blown when I saw this, because this is real observational data. And what you see, if you look carefully, there are 4 points there that are just orbiting around the center. And these are 4 giant planets, up to about 10 times the mass of Jupiter. And that outer planet is at 67 astronomical units. So just to put that in perspective, Neptune is at 30 astronomical units. So we're talking about the outer planet being more than twice the distance of Neptune in our solar system.
And I love this, because we've seen this animation so often of our own solar system with planets going around the sun.
So used to it.
This is real, this is data, and the planets go around the star. It's just wonderful.
I'm going to drag us back to our solar system, I'm afraid. Actually, this is a question which I've been wondering about since I was a kid, since we were talking about Jupiter, since I've been looking at Jupiter and thinking about Jupiter.
Are all of the rest of the questions from you?
They're all from me. But Peter Radford, who this question's from, has obviously been reading my mind. Peter, where are you? What's your question?
What is at the core of the gas planets, Jupiter and Saturn? Is it solid rock, or is it dense gas, or liquefied or frozen gas?
Yeah, when I was a kid, I used to look at pictures of Jupiter and I'm like, could I stand on that at any point? Lee, could I stand on it at any point?
This is a place where language really lets us down. I remember a reporter calling me once a few years ago and asking me if these are just big balls of gas, can't we just fly straight through them like a cloud? And the answer is a resounding no. I think the way to think about these objects is a little bit like going down to the deepest depths of the ocean. It's still a fluid, but as you go deeper and deeper into these worlds, the pressure increases, the temperature increases. So the materials that are down there are in really exotic temperature and pressure conditions.
But at what point does it stop becoming a gas and start becoming a liquid of
There's
some kind?
a smooth transition. There's not a sort of solid boundary. But I mean, going back to what we were just talking about with planet formation and the origins of worlds, the basic concept for how these giant planets formed is that you had some sort of proto-planet that was a smushy ball of rock and ice out there in the distant solar system that grew to 10 or 20 Earth masses in size and then started to accrete all the gases onto the planet. Well, that begs the question, is that rocky protoplanet still there, something you could stand on? And thankfully, we have a mission in orbit around Jupiter right now that was sent to answer that very question. We can't measure it directly. We can't go into Jupiter and find out whether it's there. So you do it indirectly by measuring the tiny little gravitational pulls on the spacecraft as it flies past Jupiter. We have to get really, really close to take those measurements, some 3,000, 4,000 kilometers above the cloud tops. But they've been doing this now for 3 years, and the answer is we still don't really understand it. There is definitely no solid boundary as a core, but there is loads and loads of heavy material down there that seems to have a gradient as you go out in radius, and we're calling it a fluffy or a diffuse core. So this is really sending Jupiter scientists and indeed planetary scientists themselves back to the drawing board to figure out what do we have to change about our ideas of solar system formation.
What do you think's in there?
Don't we talk about metallic hydrogen?
Yeah, on Jupiter and Saturn, the conditions are sufficient that hydrogen gas can be compressed so much it can be a metallic substance.
And could we do that on Earth? Could we make metallic hydrogen?
They do. Between diamond anvils, for fleeting seconds, they get some form of metallic hydrogen. Uranus and Neptune don't have metallic hydrogen, but they do have water ice crushed to this extremely exotic high temperature and pressure condition. Might be the most common form of water in the entire universe.
There you go, Peter.
Inside Uranus and Neptune.
Does that answer your question? I hope so.
It does, yeah.
It answers my 9-year-old question.
I'm very glad.
Right, we're going to move slightly further out into our solar system. This is another question from the audience. Paul Deutsch, have I pronounced your name correctly?
Yeah, that's right.
Where's Paul? Oh, there you are. Hello. Right, what's your question?
What dwarf planets, other than Pluto, do we think exist in the outer reaches of the solar system? What do we know about them, and do we think we're likely to find even more?
Maggie, what's out there?
As our technology develops and our telescopes get bigger, and we send more telescopes out into space, we are discovering more and more of these objects. And so I think the general rule of thumb is that it needs to be bigger than 900 kilometers in diameter. And so there's about 6 or 7 that fit that criteria. These are sort of small objects, a long, long way away from Earth. And so the amount of light we're receiving from them, the amount of analysis we can do of them is quite challenging. But as we do create these bigger and better telescopes, which is always a good thing for me, and we are actually detecting more of them.
The really cool thing about these dwarf planets is that they're so distant, so far away from the sun, that we often think of them as being the debris, the remnants left over from the epoch of planet formation. Yet we know so little about them because they're tiny little specks of light.
Well, the New Horizon probe,
that's right.
actually,
I was just going to say
Pluto, that's still going, isn't it?
Yeah,
still,
it is. And the funny thing about people who study these things is that the New Horizons probe went past Pluto. People were very excited to get a look at Pluto, which had this much more complicated and interesting surface than we thought. But a lot of my friends who study the outer solar system, Pluto's a bit too complicated for them. It's been processed, it's assembled into a planet. What they want is the raw material. And so New Year's Day, this year. We got signals back from New Horizons as it flew past this little thing, the team called Ultima Thule, which was this sort of skittle-shaped rock. This is the raw material of the solar system.
There we go.
But
Look,
what's interesting is that there's two bodies here. They've obviously collided and joined together, and that tells us about the kind of thing that's been happening early on, the kind of stuff that happens in your models. But it must have happened slowly for them to stick together.
Absolutely. And what's really interesting about some of these objects that we're observing is that they're actually, you might think that they're just two spheres just sticking together, but that's not actually necessarily the case. With one of these objects that we've observed, actually they look quite sort of an oval shape one way. If you actually kind of turn it one way, you actually see that it's somewhat flat, which is really, really surprising for us and actually very challenging when we're thinking about, the early stages of planet formation.
The really astonishing thing about that particular image is that it is the most distant flyby by a human-built robotic explorer ever in the history of humankind.
And the thing was so faint that when New Horizons was launched, it hadn't been discovered yet. They had to go looking for something it could fly by, and that's what they're doing now. So they're hoping, I think the odds are probably against them, but they're hoping to find another small Kuiper Belt body that New Horizons can get to as it leaves our solar system. So we might not have heard the last of it.
From the Kuiper Belt to our mystery question, I think it's Pete. I think it's if you pass it over and have a little rummage.
Hooray.
Good luck.
Good luck. Yes.
Okay. This is from Chris Hawkridge.
Chris, where are you? Here. There he is. Thank you. Here.
I'm just going to read it raw. I'm not going to read it first. If the panel had to help... it's addressed to the panel, unfortunately. If the panel had to help evacuate some humans from Earth to set up a colony elsewhere in the solar system, where would they choose and why? That's a very interesting question, isn't it? Because the obvious choices would be...
Do we get to choose who? Can we,
I was going to ask.
Choose the people we'd like to take?
Because it was my question, I'm going to choose the first one. Then we're gradually going to pick others, and you're not allowed to pick the ones that have been picked before. So I've turned the tables. So basically, well, the easiest one to get to, of course, is the moon, but there's no atmosphere on the moon. The moon.
That was the one OK.
OK, well, if we're not talking about whether it's going to be technologically possible to do or not, then I'm going to choose Titan, the moon of Saturn. It's got a thick atmosphere, it's got seas, mountains, and all the fantastic organic chemistry taking place on the surface. I think we might be able to make our home there.
It's quite chilly.
It is a little cold, but we're British.
It warms up
we're
in about 4 billion years as the sun...
Why do we have to leave the Earth again? Was there a reason?
We haven't been given a reason.
The Earth's had it. All we know, we're doomed. OK. Maggie, where are you going?
Well, I think for me it would be, because the moon's already gone, but so I think it would be Mars, sort of in the habitable zone. It used to have liquid water, sort of a hostile environment, but much more benign than the moon. And I think the potential of a colony on Mars is quite viable, so it makes a lot of sense to go to Mars.
OK, where are we now? Oh, this is a good question as well. So this is from Gary Colville. Gary, what's your question?
Yeah, well, we keep discovering new things in the universe. Is there any planet or moon, other than the planet Mars, that you personally think we should try to investigate further than we have done so far, and why do you think it? And for me, I would love to know more about Saturn's moon, Enceladus.
Saturn's moons, Enceladus. OK, so we go very quickly. I know you'll all have your favourite planets. So Lee, quickly now, you're off to Jupiter's icy moon soon with JUICE.
Yeah, not me personally.
Not you personally.
Well, I'd love to.
Yes.
We're building a robotic spacecraft right now to go to explore Ganymede and Europa. And Europa is not dissimilar from Enceladus, the moon that you were just mentioning, in that we think it's got
Here we have a picture here.
Relatively, there we go, beautiful crust of Europa is an icy shell, maybe 5 to 10 kilometres thick, and below that icy shell we think that there is a deep hidden subsurface ocean, potentially made of salt water, that, who knows, might have the right ingredients there for us to class it as being habitable. That's not to say that life exists there, it's just that it's got the right combination of an energy source, nutrients, water as a solvent, and longevity over many eons for it to be classed as a habitable environment. And I think if we were ever to discover life somewhere else in our solar system, Europa would be the place to go, and it would be the most mind-blowing scientific discovery of all time.
Europa and Warwick. obviously. Europa, Chris, where are you going to take us?
Well, there are so many places to go. We haven't been back to Venus for ages. I want to go back to a comet or two. But the mission I'm most excited about is one just selected by NASA, which is Dragonfly, which is taking us back to Titan. And Titan is Saturn's largest moon. It's got an atmosphere where it rains methane, which is rather wonderful, and it has lakes. This is the view from outside the methane clouds, but we now know that there are lakes and rivers of hydrocarbons on the surface, and Dragonfly is this octocopter. So it lands on parachute, but then unlike any mission we've sent anywhere before, it's not going to be stuck in one place. It's not even going to rove along the surface. It flies under its own power. And so the idea is that this little sort of roving insect will land, do chemical analysis, will study different sites across Titan, and then will take off and fly somewhere else a few weeks later. I just think this looks straight out of science fiction. I'm really looking forward to following this mission, and the idea of landing somewhere and then hopping off to a different site has really captured my
How big is that?
It's about the size,
drone?
it's a little bit smaller than a Mini.
Right, okay.
So it's not very big, but Titan has a thick atmosphere, so
Okay.
this sort of flying works really well.
Fantastic. Very quickly, without explanation, where do you want to go?
I'd say Uranus.
Uranus?
The Kuiper Belt.
Kuiper Belt, Pete?
Comet C 2019 Q4 Borisov, which is the first ever.
Such a show-off.
I know.
Such a show-off. I mean,
It's the first ever interstellar comet, which is just entering
Okay.
our solar system.
it's time, Chris. It's your moment of destiny.
I'm looking forward to this. Do I have to do all of them at this
You
point?
have to do every single one. Just
Every
take the whole
single
round.
one.
Let's
Okay.
do this one. This is a question from Tom and Luke, who are from Nottingham, and it says, this is a question ideally suited for me. Where are you, Tom and Luke? I owe you, thank you. Do you think we'll find increasingly complex organic molecules in space? Well, this is what I used to do for a living. So this is excellent. Yeah, one of the big surprises of the last 30 years is that we've found complex chemistry, particularly in the places where stars and planets are forming. And so we've always known that the chemistry played a role. We've had things like carbon monoxide, carbon dioxide, hydrogen cyanide, things like that. Famously, the Orion Nebula has compounds that make it smell of strawberries, if you could get enough of it. But we've begun to find more and more complex things, and my guess is we'll get to the point where we'll find amino acids in space. And what that means is when stars and planets are forming, the ingredients of life are in that environment already. Now, whether they can get down onto the surface of the planet, that's another issue. But yeah, this is really exciting, and there are new telescopes and new techniques coming online that will help us do that. So thank you for the question.
Great, thank you very much. Right, we're going to a live audience question. So I am looking for, as we are reaching the end of our time, this question is very appropriately about the end of time and the end of things. George Abraham, where's George? George, there's George, there you go. What's your question, George?
Hi, panel. So I'd like to ask the panel a question about the end of a massive star's life. So what factors in the process of going into this final stage of a massive star's life puts the outcome into three categoric possibilities? So a pulsar, a neutron star, and a black hole. Or are they not as categorically different as they seem?
Fazana, what do you think?
So I think what I'll do is I'll start by just talking about a star a bit like our sun, and then we can kind of move on to the massive star. So over time, so our sun is sort of middle-aged, it's halfway through its lifetime. In a few billion years, it will start to swell, it will start to expand and become a red giant. And then over time, it will actually develop and eventually sort of kind of collapse and become a white dwarf. And that's a very, very dense star that's essentially the mass of the sun, but the size of the Earth. But then in terms of the massive stars, Maggie, did you want to?
Yeah. So, well, I think yes. If you get stars which have a mass around sort of 10 times the mass of our sun, then things get a bit more interesting. As a star dies because the fusion that's taking place at the centre is usually when the star is sort of alive and kicking, is balanced out by the gravitational pull. So you've got fusion at the centre pushing outwards. You've got gravitational pull pulling inwards. But as it consumes its fuel, it gets less efficient, and so the gravity starts to overwhelm it. And so you get these larger stars sort of collapsing in on themselves. And I think the demise of the star will be very much dependent on the mass of the star. Sort of the more massive, sort of the more that gravitational pull is, sucking everything in. So I think that that really governs the outcomes of where it's going to go. Will it turn into a black hole? So the more massive things will turn into a black hole.
Where does the supernova come into this, in terms of the actual death?
So what's going on here is when you form a white dwarf, it's to do with electrons don't like being crammed close together, and so that supports a white dwarf. If you have a more massive star, that pressure, once you turn off fusion at the centre, means that everything rushes towards the centre. You get a bang, that's the supernova, and most of the material shoots outwards. But
and of course we can see these, of course.
Yeah,
we can see,
and we see this bright explosion. Although what you're seeing in the explosion for a supernova is the radioactive decay of elements that are created in the explosion. But right at the centre, you overcome that electron pressure and you end up with a thing made of neutrons. So that's your neutron star. Some of those are pulsars if we happen to be in the right direction to see them. But if you have an even more massive star, even the neutrons get pressed together and then there's nothing to stop it collapsing to a black hole. And then there's a special case, we think, stars about 120 times the mass of the sun, which may only have existed in the really early years of the universe. The way the physics works out is that they just blow themselves to bits and you get nothing left whatsoever.
Pete, are we likely ever to see a supernova doing its thing, do you think? I mean, is it a possibility?
It's difficult to predict.
Which star would we be looking at?
Okay, it's difficult to predict where a supernova is going to happen, but there are people who regularly monitor galaxies to try and pick up supernova events, and then all the eyes turn, all the telescopes turn on them to do the rapid analysis they can before the supernova fades away. But in terms of likely to go off, I mean, the classic one is Betelgeuse. It'll be in the northeast corner of Orion.
Orion's shoulder.
Yeah, Betelgeuse actually means armpit of the central one, so I'll leave it as Betelgeuse. But basically, that's often cited as being a star which is likely to go off as a supernova. But in reality, we're probably looking at anywhere between now and maybe 100,000, maybe even longer time scale for it to actually go off. And that does beg the question as to whether, that would actually present us any difficulty here on Earth. And I do remember, actually, it was a funny story about it was a researcher looking into the impacts of a close supernova going off on a Sky at Night program many years ago, and he did a bit of analysis on a star called, I think it's IK Pegasi, which is the closest, or was the closest candidate thought to be able to go off as a supernova. Now I think it's not likely to go off that way, but at that time it thought it might, and he did his analysis and he sort of did loads and loads of calculations and then looked up and said, I think it'll be possibly dangerous for an unshielded human. So basically, if it looks like Betelgeuse is going to go off, make sure you're wearing a coat.
Okay, right. What would it look like? I mean, if we were standing here and it went off, what would we see?
Betelgeuse, you'd see it in the daytime. It would be brighter than anything else in the sky.
Really bright. It'd be obviously very bright. It'll probably be as bright. I think the figures which have come out for Betelgeuse going off are about as bright as the full moon.
And are we allowed to call it Betelgeuse?
Call it what you like.
Can we call it, or is there a ferocious debate about Betelgeuse?
No, I think we're all wrong as English speakers, however we say it. So
right.
you
Alpha
take your pick.
Orionis.
Okay, there you go. Well, like a dying star, sadly, we have come to the end of our time. I'd like to just give our audience here at the University of Warwick a huge round of applause. Thank you very much for coming. It's been such a pleasure. And of course, our wonderful panel, please give them a huge round of applause. Thank you very much indeed. Well done. And thank you very much to you at home. We will see you back on your screens very shortly, and from us on the Sky at Night, it's time to say good night.